I am Sheikh Rashidul Rahman, Assistant Professor, Department of Electrical and Electronic Engineering. So today I am going to discuss about the topic of fault analysis. So today my lecture is being about to fault analysis. So fault means any abnormal condition which is not required and which is not acceptable. So in power system, if there is any abnormal condition for which the power transmission being hampered, this is called fault condition. So fault mainly two types. One is short circuit and another one is open circuit. So in open circuit, the amount of current flow is zero. But in short circuit fault, there should be a large amount of current that flowing through the line, and it can be enough to damage any device. So that's why here we will discuss about short circuit fault. Now in power system, mainly there are two types of fault. One is symmetrical fault, another one is unsymmetrical fault. So symmetrical fault means if in three-phase transmission line, the amount of current flow in three lines are equal, or the same types of fault occur in every line, each and every line, that is called symmetrical fault. It means that three line or three phase may be short circuited or three phase may be open circuited. So this is called symmetrical fault, when each and every line has the same condition. Unsymmetrical fault means each and every line is not the same condition. Maybe one or two line is in fault condition, short circuit fault, another one is as keep as it is. It means that it is okay. So this type of fault is unsymmetrical fault. So in symmetrical fault, the system remains balanced, but in unsymmetrical fault, system no longer in balanced state. It is unbalanced condition. So there are some example of unsymmetrical fault like single line to ground fault, or line to line fault, or double line to ground fault, etc. So in our transmission line or high voltage line, about 75% of all faults in power systems are either transient or permanent single line to ground fault. So most common fault in transmission line is single line to ground fault. It means one line short circuited to ground. That is the most common fault. But most severe fault is the three phase symmetrical short circuit fault. So when three phase goes to short circuit, that contains more current. So this is the more severe fault actually. So in short circuit, there should be a high current flow, and this high current can be damage the connected device. So we need to calculate the maximum short circuit current to ensure the rating of our protecting device, so that our protecting device like circuit breaker, fuse, or relay can be operated in such a large current. So this is the transient analysis of RL circuit. So in this transient analysis, the final equation of current I should be the AC component plus DC component. So whenever we switch on the circuit, this is the partial inductive or capacitive circuit, there should be two current exist initial time. One is the AC component and another one is the DC component. So the equation of DC component is C, this is a constant, e to the power minus small t by capital C. So this E is the exponential term, small t is the time, and capital T is the time period. So this is a decay current that will be eliminated from the circuit after some time. So now in our transient or in the total period, so in the current envelope with respect of time, there should be almost three peaks. One is the initial high peak that is called the subtransient current, and this peak is the subtransient period. And next, this is the transient period. So this is the next lower peak. And finally, this is the steady state period, which means the current will flow a constant rate, or let's give a constant peak, that is the steady state period. So three categorize, we can classify current in three category from the switching to ongoing condition. So if we calculate the subtransient current or the most high peak current, we can denote is double prime. So I double prime, that is the OC divided by root 3. OC is the high peak. This is the maximum voltage. And if we want to calculate the RMS value, we have to divide it by root 2. And this XD double prime is the subtransient reactance. And if we can calculate the transient current, or we want to calculate the transient current, that should be OB by root 3. That is the OB is the second high maximum peak. And this is the root 2 is means we want to calculate the RMS value. So XD prime is the transient reactance, and finally XD is the steady state reactance, and that should be EG divided by XD. This is the steady state current. So EG is the internal voltage, or it means that OA. This is the steady state period peak value. If we divide it by root 2, we will get the RMS value. So now this is a mathematical problem. So there is a question: a 100 MVA 13.8 kV Y connected 3-phase 60 Hz synchronous generator is operating at the rated voltage and no load when a 3-phase fault occurs at its terminal. So it reactances per unit to the machine's own base, that is the subtransient, transient, and steady state reactance are given. The time constant for transient and subtransient are also given. So the initial DC component is the 50% of the AC component. Now we have to find out at first what is the AC component of current. At the instant of initiating fault, what is the AC component of current? So the reactances are given here in per unit. That's why we have to convert the rating with in the per unit rating or into the per unit rating. After that, we have to solve the transient or subtransient current, and finally we'll convert the per unit current to its real base value, that is the ampere value. So here the rating is given 100 MVA and 13.8 kilovolts. So we can choose our base power 100 MVA and our base voltage 13.8 kilovolt. So if we choose our base power 100 MVA and base voltage 13.8 kilovolt, then the base current should be base power divided by root 3 into base voltage, that is 4184 ampere. So the subtransient, transient, and steady state current, we can easily calculate. The equation should be voltage divided by subtransient reactance whenever we calculate the subtransient current. So here the generator is operated at the rated voltage, and the voltage rating is 13.8 kilovolt. So that's why the per unit voltage should be 13.8 divided by 13.8 kilovolt. That means 1 per unit. So here voltage is 1 per unit, and this is the subtransient reactance. So we can find out the subtransient current. And for transient reactance, we can find the transient current, and for steady state reactance, we will find the steady state current. Now, the first part of our question is we have to find out the initial short circuit current or subtransient current. So initial subtransient current should be, that is the 34,900 ampere. And our second question is, what is the total current, that is AC plus DC, at the right after the fault? So AC plus DC. So we know in our question it is given that the initial DC component is 50% of its AC component. So that's why we have to find out the initial AC plus DC current, that is the AC current plus 50% of its AC component. So that is 1.5 times of subtransient current. Then we can find out the initial AC plus DC current, that is the 52,350 ampere. And finally, the third question is, what will the AC component of the current after 2 cycle and after 5 seconds? So what will be the AC component of current? So what will be the AC component of current? So this is the equation, that is subtransient minus transient current e to the power minus, this is the decay part, and transient minus steady state, and finally this is the steady state current. So we can easily calculate, all values are given here. So now after 2 cycle, it means that this is a 60 hertz system. So after 2 cycle, it's 2 by 60, then we will find out this 1 by 30. So 2 by 60, it means that 1 by 30. So if we put the values, that is the time constant t is given in the question, we'll find out the answer. And after 5 seconds, it means that we have to put the small t value is 5. Then finally we'll get the last answer. So this is the next problem. So the question for this particular mathematical problem is, two generators are connected in parallel to the low voltage side of a transformer. Generators Z1 and Z2 are each rated at 50 MVA, 13.8 kV, and with subtransient reactance of 0.2 per unit. Transformer T1 is rated at 100 MVA, 13.8, 115 kV, with a series reactance of 0.08 per unit and negligible resistance. So these two generators are connected in parallel and their rating are given here. And here a transformer is connected with series with these two generators. The transformer rating is also given here. Now, in initial high voltage side of the transformer, the voltage is 120 kilovolt and transformer is unloaded. Then there is no circulating current flowing in the transformer. We have to calculate the three-phase short circuit fault current whenever a three-phase short circuit fault occurs at the high voltage side of this transformer. So to solve the math, again, the reactances are given in per unit, and these are given in the machine own ratings. Now, the we have option. We can choose the base value of power, either 50 MVA or 100 MVA, or 13.8 kV for the base voltage, or 115 kV for the base voltage. We have option actually. So in this math, we solve this math by considering the transformer rating as the base rating. So the base power is 100 MVA and base voltage at the high tension side of the transformer is 115 kilovolt. So now the new base reactance for the generator we have to calculate, because the generator reactance is given 0.20 per unit at their own machine rating, and for their own machine rating the power rating is 50 MVA, but now we have considered the power is 100 MVA base. So that's why we need to convert the old reactance of generators to the new reactance of the new machine base. So this is the formula how we can convert the old reactance to new reactance of new rating. After that, we can calculate the internal voltage of the machine. that is the fault voltage. This is the unloaded condition actually. So the transformer are connected without load. Transformer are connected to the generator only. So whenever the fault was occurred at the high tension side of the transformer, the fault voltage is 120 kilovolt. It means that this voltage should be supplied by the generator. So that's why the generator internal voltage should be 120 kilovolts. So the per unit voltage is, we have to divide this 120 by 115 kilovolt. This 115 is the base value. So 1.044 per unit is the internal voltage of the generator. Now, there are two generators connected to the parallel condition. So we know the in parallel system, the voltage would be same. So that's why two generators will be operated at same voltage, that is 1.044 angle 0 degree per unit. And these are the reactance of the generator, and this is the J0.08 is the transformer reactance. So now the high tension side of the transformer, there was a three-phase short circuit fault. So if we want to calculate the short circuit current, the easy approach is, if we can find out the voltage V1, this one node, then we can easily multiply this voltage with the admittance of the transformer. Then we can calculate the short circuit current. So we need to convert the source. So if we convert the source, then the short circuit current should be voltage divided by Thevenin impedance. So this is the internal voltage of the generator, and this is the reactance of the generator. So 2.61 angle minus 90 degree is the generated current. So this is the two generated source current. We just convert the voltage source to the current source. And here this is the C parallel admittance of the generator, which in previous case that was the series reactance. And here if we inverse the series reactance, that is 1 by J.4, we can get minus J2.5. This is the parallel admittance. And this is same, the parallel admittance, this is the admittance of the transformer. If we inverse the transformer reactance, we can find out this admittance. So now we have to apply a nodal analysis of node 1. So if we apply this a nodal analysis, then the entering current, that is the Kirchhoff's current law, should be equal to the leaving current of this particular node. So entering current of this node is the two current source, and the leaving current from this node is the three parallel branch. So if we calculate this, we can find out the voltage V1, that is the node voltage. And if we multiply this voltage to the admittance of the transformer, we will find out the short circuit current. And now this is the per unit value. So we have to convert this value to the real unit. So we have to multiply this with the base value. So whenever we multiply this with the base value, we can finally find out the short circuit current. So this is the full answer. So this is the internal generated voltage of loaded machine under transient condition. So if a generator is connected to a load with external branch, then if a fault, that is the three-phase short circuit fault, occur at the terminal, that is the load terminal, then the internal voltage equation of the generator should be the all drops of this series circuit. So all drops means this is the terminal voltage plus the internal drop. So the terminal voltage Vt should be the fault voltage plus the external drop. So this terminal voltage Vt, the equation of Vt should be the fault voltage plus the external drop. And if we want to calculate the internal voltage of generator, we have to add internal drop with this terminal voltage of the generator. So internal drop means the drop across the synchronous reactance and drop across the armature resistance, Ra and Xs. So if we neglect the armature resistance, if it is a negligible value, then our equation finally should be terminal voltage plus internal drop. So now this voltage, internal voltage, we can find out for transient condition and subtransient condition, steady state condition also. The only one difference is the reactance is just shifted from for transient condition, that is the transient reactance, for subtransient condition that should be subtransient reactance, and steady state condition that should be steady state reactance. And for motor, this is the reverse of generator. So that's why we have to subtract the internal drop from the terminal voltage. For generator, we have to add the internal drop with the terminal voltage, and for motor we have to subtract the internal drop of the motor from the terminal voltage of the motor. So this is the equation. So now this is the math. This is the mathematical problem. Here the question is 100 MVA 13.8 kilovolt 0.9 power factor lagging Y connected 3-phase 60 Hz synchronous generator is operating at rated voltage and full load when a symmetrical 3-phase fault occurs at its terminal. So it is operated at rated condition when a symmetrical 3-phase short circuit fault occurs at its terminal. So the reactance per unit to the machine own base is given here. That is the subtransient, transient, and steady state reactance. First question: if the generator operates at full load when the fault develops, what is the subtransient fault current produced by the generator? So generator operated at full load conditions. So what is the subtransient fault current? So again, the rating is given here 100 MV and 13.8 kV. So we have considered this given rating as our base value. So that's why our base power is 100 MVA and base voltage is 13.8 kilovolt. So this base rating, we can calculate our base current, that is 4184 ampere. Now, when loaded condition, what is the subtransient current actually? So that's why we have to find out the load current. So the rated voltage is 13.8 kilovolt and rated power is 100 MVA, and the device is operated, generator is operated at this condition. So that's why the current should be 1 ampere. So in rated condition, current should be 1 ampere. That is 1 ampere means 1 per unit actually, because we have to convert this as per unit. So whenever you convert the power, that should be 100 MVA divided by 100 MVA, that is 1 per unit power. Whenever we convert the voltage, there should be 13.8 kV divided by 13.8 kV, that should be 1 per unit voltage. So this 1 per unit voltage, 1 per unit power, the current should be 1 per unit. And this angle we find out by the power factor angle, and this is the lagging power factor, so there is the minus. So the internal voltage is the fault voltage plus the internal drop. So the terminal voltage is the fault voltage, and the fault voltage is here 1 per unit, because in question given the 3-phase fault whenever occurred, generator is operated at the rated condition. It means 13.8 kilovolt is the fault voltage. So that should be the fault voltage per unit, or the terminal voltage is 1 per unit, angle 0 degree. And this is the internal drop, that is the subtransient reactance, and this is the current. So we can find out easily the internal voltage of the machine. Now the short circuit current, it means that we have to divide the internal voltage by the subtransient reactance. So this is the subtransient reactance J.12. Then we can find out the subtransient per unit fault current. If we multiply this with the base value, we can convert this per unit current to the ampere value. So this is question number A. Now the question number B is, if the generator operates at no load and rated voltage when the fault develops, what is the subtransient fault current produced by the generator? So now this is the no load condition. So if there is no load, it means the load current is 0. So armature current I should be 0. So the internal voltage should be the fault voltage, that is 1 per unit. So the subtransient fault current should be the internal voltage divided by subtransient reactance. So finally we can get the value as per unit, and if we multiply this with the base value, we can convert it as ampere. And the third question is, how much difference does calculating the voltage behind subtransient reactance make in the fault current calculation? So what is the difference actually? No load to full load current difference. So here the full load current is greater compared to no load. So that's why the full load minus no load divided by no load into 100%. So the difference is 5.76%. So here in our question, only subtransient current have to be calculated because question asks to calculate the subtransient current, and the difference between no load to full load in subtransient condition. That's why we use only subtransient reactance. But if the question has asked to solve the current for transient period or steady state period, then we have to use this transient or steady state reactance. So we can use this value as the demand of the question. Well, now this is another example. So a synchronous generator and motor are rated 30,000 kilovolt ampere, 13.28 kilovolt, and both have subtransient reactance of 20%. So here there is a generator and a motor, and their subtransient reactance is 20% based on their rating. The line is connected between these two machines, and the reactance of the line is 10%. Now, the load specification is given here. That is, the motor is drawing 20,000 kilowatt power at 0.8 leading power factor, and the terminal voltage, that is the 12.8 kilovolt. So now when a symmetrical three-phase fault occurs at the motor terminal, we have to find out the subtransient current in the generator and the motor and the total fault current. So we have to calculate the subtransient current for the generator, we have to calculate subtransient current for the motor, and finally we have to find out the total fault current. So here the rating is given 30,000 kilovolt ampere and 13.28 kilovolt. So we can easily consider these as our base value. And in terms of this base value, we can easily find out our base current, that is 1310 ampere. Now, whenever the fault is occurred at the motor terminal, the voltage is 12.8 kilovolt. It means that the fault voltage is 12.8 kilovolts. So we have to convert this voltage to per unit voltage because reactances are given here in per unit. So that's why we have to convert this voltage to per unit voltage. So whenever we convert the fault voltage by the base value of voltage, the per unit is 0.97 angle 0 degree. Now we have to find out the internal voltage of the generator. So the internal voltage equation is terminal voltage plus internal drop. And the terminal voltage Vt, this equation should be the fault voltage plus the external branch drop. So fault voltage is 0.97 per unit, and the external voltage means current into external reactance. So current, that is the 0.69 plus J0.52, and the reactance of external branch is J0.1. So if we calculate this, we can find out the terminal voltage of the generator. Now, if we add the internal drop with this terminal voltage, we can easily find out the internal voltage of the generator. So whenever we consider the internal drop to add this terminal voltage, so internal drop means current into the internal reactance of the generator, and the internal reactance of the generator is 20%, means J0.2. So easily we can find out the internal voltage of the generator. So if we divide this internal voltage of the generator by the reactance, we can find out the subtransient current. Now, just look at the figure B. Whenever a three-phase short circuit fault occur at the motor terminal, that is at P point, then whenever we want to calculate the short circuit current which flow from the generator, then the reactance is passes through the current is 2 reactance. Number of reactance is 2. First, J0.2, this is the internal reactance of the generator. Next, the external branch reactance J0.1. So these two reactants are connected in series. So we can add these two reactants. So the total reactance should be J0.3. These reactants have to consider whenever we want to calculate the short circuit current from the generator. So that's why the internal voltage of the generator divided by the reactance J0.3, and finally we find out the current flowing from the generator at short circuit period. Now for motor condition, for motor we know the terminal voltage is the fault voltage, that is 0.97 per unit, And for motor, we have to subtract the internal drop from the terminal voltage. Then we finally find out the internal voltage of the motor. Now the short circuit current of the motor is the internal voltage of the motor divided by the reactance. And here only J.2, that is the internal reactance of the motor, will be considered, because the current flowing with the internal reactance and goes the short circuit branch. So this only one reactance will be considered. So that's why the internal, that is the subtransient short circuit current for the motor is the internal voltage of the motor divided by the reactance J.2. Then we can find out the short circuit current for the motor. And if we sum these two current or add these two current, we will find out the total short circuit current. And remember, we have to multiply the per unit current with the base value to convert the real unit or ampere unit short circuit current. So our next topic is the fault current calculations using the impedance matrix.